Welcome back, everybody, to lesson 4.4 about parametric functions. This is going to be a new way for you guys to define a function in the coordinate plane. So let's get cooking and look at parametric functions. So the reason really that we're talking about this in this section is if you've noticed all of the conics that we've drawn, not all, there's some parabolas that did, but almost all of the conics that we've drawn didn't pass the vertical line test. You guys probably learned in middle school for defining a function. So, but what all of them do have in common, and what every function in the coordinate plane has in common, is that it's a relationship between a collection of points, x comma y, where x is the y coordinate of the point and y is the y coordinate. X is the x coordinate of the point, y is the y coordinate of the point. So what we're going to do is we're going to define something called a plane curve parametrically by defining the x and y coordinates separately in terms of a parameter. So what that looks like is this. If we let x be defined by some function f of t, and y be defined by some function g of t for t within this interval from a to b, then the collection of all the points that are defined by that relationship would be f of t, g of t. So this is what's called a parametric function with t as its parameter, because you notice t is what I can plug into each one of these functions to get an x coordinate and to get a y coordinate. And usually when we do this in context, t usually denotes time, which is why we typically use t as the parameter. And we'll look at an example of that at the end when we look at projectile motion. So basically what happens here is this means there's a function that defines the x coordinate and then a function that defines the y coordinate, and both of those functions have the same input value. Well, the input parameter, which is t in this case. All right, so let's take a look at an example of a parametric function. So right here is an example of a parametric function where the x coordinate is defined by 3t squared and the y coordinate is defined by 2t for any t value that is between -2 and 2. So right here, we look at this and we say, if these are the t values, if I plug -2 into the x function, I get 12. If I plug it into the y function, I get -4. And if I go and continue to do that in each one of these functions, I get a set of points. So I'm going to start here. I notice I have a point at 0, 0. I have points at 3, -2, and 3, 2. So I've got points at 3, -2, and 3, 2. And then I also have points at 12, 4, and 12, -4. So if I notice what this function actually looks like, is it looks like a parabola. So this is an example of a parabola defined with a parametric function. I also notice here this says -2 is less than or equal to t, which is less than or equal to 2. So this would actually be the entirety of this function. So it would be a portion of a parabola. All right, so let's take a look at how we could write this in our typical rectangular or Cartesian form that we're used to seeing. So for this one, I noticed this would actually be pretty simple to solve for the parameter, which is t in this case, and then substitute it back in to get an equation. So what I could do here is I noticed that if y is equal to 2t, then t is equal to y over 2. All right, another thing that I also kind of want to keep in mind at the end is I notice if -2 is less than or equal to t, which is less than or equal to 2, then when I'm done defining this, if y is equal to 2t, then -4 would have to be less than or equal to y, which would be less than or equal to 4, which actually, if we go back and look at this parabola right here, that's exactly what we have. We have all the y values between -4 and 4 that are defined. All right, so now that I have t in terms of y, I can substitute it back in. So x equals 3t squared. If t is equal to y over 2, then x is equal to 3 times y over 2 squared. So then x will be equal to 3/4 y squared. And if you notice, this is now that equation of the parabola that we had. This is y squared, so it's going to open to the right. This is a positive 3/4, so it's going to be, or sorry, this is y squared, so it's opening either right or left. This is positive, so it opens right. If 3/4 is equal to 4a, then a is equal to 16 over 3, which means this will help us define where the focus of the parabola is at. And I also notice this is centered at the origin with its axis of symmetry along the y-axis, which is exactly what I have in this picture right here. This portion of the parabola is exactly what was just described by this equation of a parabola. So this is one way that we could take something that is in that is in parametric form and write it in rectangular form or Cartesian form. All right, so let's take a look at another example where it won't be as easy to do this algebraically. So if we say that the x coordinate is defined by a cosine of t and that the y coordinate is defined by a sine of t. This one is not really as easy to just isolate t, because if I tried to do it over here, I'd have cosine inverse of x over a. It's not going to look nice when I substitute back in here. Here I would have sine inverse of y over a, which again would not look nice if I plugged it back in over here. So instead what I'm going to do is I'm going to notice, all right, I've got sine and cosine involved. So if I've got sine and cosine involved, then I can remember there's a Pythagorean identity that I can use that says sine squared of t plus cosine squared of t is equal to 1. What I want to do first is I want to isolate sine of t and cosine of t. So then cosine of t would be equal to x over a, and sine of t would be equal to y over a. So now that I have these isolated, I could plug them back into the equation down here, and this would be y over a squared plus x over a squared is equal to 1. So then this would be x squared over a squared. I'm switching these two because it's going to look more familiar if I do it like this. Plus y squared over a squared equals 1. Now if I multiply everything by a squared, I'm left with x squared plus y squared equals a squared. And you should recognize this as the equation of a circle with a radius of a. So this would be another way that I could take a parametric function and rewrite it in terms of rectangular coordinates. When you're doing this, you're going to have to come up with a strategy and try to figure out some way to define it with its rectangular coordinates as opposed to the parametric coordinates that I have here. Not always a necessity. In fact, you don't really have to do that, but this is one way that I could define this function. All right. So this is what I really ultimately wanted to get to today, because this is the main application of parametric functions, and that's projectile motion. So you will probably learn about this in physics. If you are taking physics, you may have already learned about it. So what we're going to do is we're going to take t and define it as the amount of time elapsed from the initial point of impact for an object. So what we can use is a parametric function that describes the object's motion like this, where x equals initial v, so this is v naught, v null, that's typically used to denote initial, times cosine of a times t, and then the y coordinate would be 0.5 gt squared. 0.5 is also 1/2. 0.5 gt squared plus v null sine of at plus h. So there's a lot of variables. Remember, t is the parameter. So t is what all this is actually going to be in terms of. So we need to define v null. So v null is the initial velocity. It's the velocity that this thing is initially hit at, launched at, whatever it is the initial velocity. A is the launch angle of the projectile relative to the horizontal. So A is the launch angle of the projectile. G is the force of acceleration. The reason that we use G is because on Earth, this force of acceleration is typically negative 9.8 meters per second squared. So we're going to use G here for gravity. So this is going to be negative 9.8 meters per second squared. And then H is the initial height. It's whatever height the projectile starts at. So we're going to take a quick look at a problem. We're not going to completely solve the problem, but we're going to take a look at it. We'll finish solving it in class. So Dustin Johnson, who just won the Masters, hits a golf ball at an angle of 30 degrees with an initial velocity of 82 meters per second. So we're going to first write a parametric equation to model the situation. So we're going to go back and say, all right, the x coordinate is defined as v null cosine of a t. So I'm going to go over here. So the initial velocity is 82, and this is the x coordinate. So 82 cosine of 30 times t. All right, so cosine of 30, if you think back to your unit circle, do you remember what cosine of 30 is? I'm gonna give you a second. All right, good, it's square root of 3 over 2. So then x is gonna be 41 square root of 3t. So this is how I can define the x coordinate of this golf ball, which is the horizontal distance of the golf ball at any moment in time. So then the y coordinate, so the y coordinate is 0.5 gt squared plus all of this stuff. So this would be 0.5 times negative 9.8 right here would be negative 4.9. So this would, oops, went the wrong way. So this would be negative 4.9 t squared plus the initial velocity, 82 times sine of 30 times t plus the initial height in this case, we're going to assume because it's a golf ball that he hit it off the ground. So we're just going to go back and check initial velocity times sine of 30 plus h. And in this case, h is 0. All right. So then when I simplify this, y equals negative 4.9 t squared plus 41t. All right. So this is the vertical distance of the ball, and it's defined by this negative 4.9 t squared plus 41t. So at any point in time, I can plug in a value for t, and it'll tell me that after that many seconds, where is the horizontal distance of the ball and what is the vertical distance of the ball. So how long was the ball in the air? So this is a fantastic question. How long was the ball in the air? Typically, we would define the ball as no longer being in the air when it hits the ground again. So if we notice the initial height here is 0, so I want to figure out when this is equal to 0 again. So then 0 would be equal to negative 4.9 t squared plus 41t. So to figure out how long the ball was in the air, I would factor out, well, I could just factor out a t here. So let's say that this is t times negative 4.9 t plus 41. So then to solve this, I notice that one solution is when t is 0, and then also when it's equal to 41 over 4.9. So this one, I notice this is the value that is after the initial impact. So this is when the ball will hit the ground again. So then if we assume the ground is completely flat, we're going to leave this up to us to do in class. How far does the ball travel before it hits the ground? Basically, what we would do is we would take this value for t and plug it into the x coordinate, because remember, this is the horizontal distance, how far the ball has actually traveled. And that would give me how far it's traveled before it hits the ground. So that is it for today. Today we talked about parametric functions and how they're defined. And then we talked a little bit about how to write them in rectangular form. And then we also talked about projectile motion. So I hope you took some good notes. If you have any questions, please ask them in class, and I hope you have a fantastic day. I'll see you in the next video.